Hello and welcome. I'm going to be talking to you about selective discharge. This is a topic in one of the parts of topic 19, and it's the HL redox material you need to know about electrolytic cells, or one of the things you need to know about electrolytic cells. Selective discharge deals with the fact that at an anode and cathode in an electrolytic cell, so an anode and cathode in an electrolytic cell, so notice positive anode, negative cathode, and electrolytic, we have multiple reactions that can occur. This usually happens because we're in solution, so either the hydrolysis or electrolysis of water can happen, or the electrolysis of whatever salt you have that's in solution can happen. And so you get two reactions of the anode, two reactions of the cathode, and you have to decide who wins, which one actually happens, based on these three factors: electrode potential, relative concentrations, nature of electrode. We saw one pretty straightforward example of this with very dilute solution of magnesium chloride. So I'd have magnesium chloride in solution. And what would be the other thing in here? Well, of course, I would have lots and lots and lots of water because the solution was very dilute. All right, so the two options at my anode would be the anode is always oxidation, so I could either have the oxidation of water, 2H2O yields 4H plus oxygen gas plus 4 electrons. You should, of course, always write state symbols next to everything. I'm being a little lazy here because I want things to fit. The other thing that could happen at the anode is the oxidation that would happen within MgCl2. If I want to check what the oxidation would be there, well, I'm going to check my two ions forming elemental states, which is what happens in electrolysis. And magnesium, in order to form solid magnesium, would have to be reduced, gained 2 electrons to go from an oxidation state of +2 to 0. Chlorine would have to be oxidized. 2 chlorines would be oxidized to go from an oxidation state of -1 to 0, becoming less negative, more positive. So oxidation, reduction, the two reactions that would happen to go from the compound MgCl2, electrolyze that compound to form my two elemental states. All right, so at my oxidation, the competing reaction would be the oxidation of chlorine, Cl2 plus 2 electrons. At the cathode, of course, I have the reduction of water. Water plus 2 electrons yields H2 gas plus 2OH minus, or the reduction that would happen from MgCl2. Mg2 plus 2 electrons yields Mg solid. So in this case, when I'm trying to decide who wins, well, the thing that really matters is relative concentrations. This is one example of when relative concentrations is going to matter. And in this example, because I have a very dilute solution, the thing that wins at both the anode and the cathode is going to be water. And so my product will be the products that I get in water. And so the products that I have, well, I would observe oxygen gas coming out of the anode, that's from right here, and hydrogen gas right here coming out of the cathode. The other thing you could mention, it didn't show up in the answer key here, but we have at the anode, I have H plus being released, and so the pH would go down. Here I have OH minus being released, and so the pH would go up around the cathode. All right, so that's one example of selective discharge. I think a pretty straightforward one, dealing with relative concentrations. We're going to talk about each of these in terms of specific examples right now. All right, so the first thing, relative electrode potentials, and we get relative electrode potentials in the data booklet, and it is section 24. So I'm going to open up section 24, standard electrode potentials at 298K. That Plimsoll, of course, means standard. All right, the biggest thing to know about using electrode potentials with redox reactions is, first of all, of course, we're seeing the reactions written as reductions. We're seeing the adding electrons on the left. And then the more positive the standard electrode potential means you're more likely to be reduced. And you use the more positive values that are shown in the data booklet. And here's where I think I misspoke in class, and I'm sorry to have caused confusion. You use the more positive electrode potentials that they give you in the data booklet. So the more positive I am, the more likely I am to be reduced. Of course, that means the more negative I am, the more likely I am to be oxidized. All right, and I never change the E0 values. The E0 values are what they are. We don't scale based on number of total electrons. So what will this look like? Let's look at example 1. Example 1 is the electrolysis of NaOH aqueous. So if I'm looking at NaOH aqueous, and I have my setup here, and I have my positive, negative. Well, I would have the negative, of course, is the anode oxidation. Oh, excuse me. Let me make it the same that it is as the one we just looked at. So let's do, oops. I just want to make sure it's exactly the same as what we just saw. So we have here negative, cathode, reduction, positive, anode, oxidation. I'm showing you this because I would recommend writing this out each time. All right, so I'm going to have Na plus and OH minus. Well, if I'm going to go from positive to Na solid, that's +1 to 0. I'm becoming more negative. That's going to be reduction. So the two things that will compete, the reduction of water or the reduction of Na plus, the two things that will compete for oxidation are the oxidation of OH minus or the oxidation, of course, of water. In both cases, we're competing with water because we have an aqueous solution. So I could either get the reduction of, let me grab a new color. I could either get the reduction of water or the reduction of Na plus. And at the anode, I could get the oxidation of water or the oxidation of OH minus. I could get one or the other. Before we saw in both cases, water wins, but you don't have to have the same thing win at both electrodes. So by that I mean, if water wins at the cathode, if water is what is preferred at the cathode, it doesn't also have to be preferred at the anode. So it could be that water wins here, OH minus wins here, vice versa. So let's get into it. So in this example, they don't give us anything about very dilute or anything like that. So they're not giving us any indication. They're just telling us the electrolysis of NaOH aqueous. They're not giving us any indication that we should worry about relative concentrations. And so in this case, they also don't tell us anything about the nature of the electrode. So in this case, I'm being clued in to think about relative electrode potential because they don't give me any information about anything else. All right, so at the cathode, let me show this in a way that makes sense. At the cathode, I have two possible reactions. I either have the reduction of Na or the reduction of H2O. At the anode, I have the oxidation of water or the oxidation of OH minus. Where did I get that? Well, I looked in section 24. I found OH minus, and OH minus I see right here. And I check to see what it looks like when it gets oxidized. So left to right, it shows me what happens when it gets reduced, and so right to left shows me what happens when it gets oxidized. You'll notice in this example here, they just scaled up so that their electrons balance, but the important thing is that they did not change the electrode potential. All right, here's where we have to pay really, really close attention, and it does get a little tricky. So let's remind ourselves, the more positive E naught value is reduced, and the more negative is oxidized. The more positive is reduced, the more negative is oxidized. All right, so at the cathode, I know the thing that's going to happen is reduction. I know for sure the thing that's going to happen is reduction. So I'm looking for who's more positive, and that's the reaction that's going to win because that's the one that's going to be reduced. More positive gets reduced. All right, so more positive in this case is negative 0.83, and so water wins. Water is preferentially reduced, or water is the thing that actually does the redox reaction, and so the products that I would expect, H2 gas and OH minus. Okay, at the anode, the first thing that I look at is the electrode potentials and I identify where they are. So I have here's my OH minus, and here is my water, and I need to be really careful to find the right water. And this is the right water because this is the one where water is alone and it forms the things that it forms when water gets oxidized. So identify my two equations. All right, so the more positive would get reduced. So this is more positive. And here's where, and I'm sorry if I misspoke in class and caused any confusion, we don't change any signs yet. So all I'm trying to figure out is who's going to get reduced, who's going to get oxidized. So water in this case, if I'm competing between OH minus and water, water is more likely to get reduced. OH minus is more likely to get oxidized. I'm at the anode, so I'm looking for whoever wins in terms of oxidation or whoever is more likely to get oxidized. The one that's more likely to get oxidized, well, that's actually OH minus. All right, so in both cases here, I used a standard electrode potential. I found out who was more positive and who was more negative. The more positive gets reduced, and so the more positive is the one who wins at the cathode. The more negative gets oxidized, and so I'm looking for who's ever more negative, and more negative in terms of standard electrode potential, and that's the species that's going to get oxidized. That's who I decide who gets oxidized. Now, when I actually rate the reaction, when I rate the two reactions that could possibly happen, the thing that happened here was they're switching the signs because this shows reduction. And so if I'm showing oxidation, if OH minus is my reactant, I need to switch this sign. But the thing that I always compare is the electrode potentials I find in the data booklet. This is what I use for comparison, in order to figure out who gets oxidized, who gets reduced. It's not that different than using the activity series to figure out who gets oxidized or who gets reduced. If you're higher, you're more likely to get oxidized. It's just a more specific, more accurate way to actually figure out who's going to get oxidized, who's going to get reduced. All right, so I have the two reactions that are winners, and so I see that overall, and they've balanced out their equation here, so they've taken all of these reactants, all of these products, these reactants, these products, given us this overall reaction. And so overall I get H2 gas and O2 gas, H2 gas from right here, O2 gas from right here. The thing that the textbook kind of made a little bit of a mistake on is right here. H plus is not released. What's actually happening is that OH minus is reacting. OH minus is reacting. And so that does decrease the pH because you have less OH minus. And so we can also talk about the pH at the anode and cathode. At the cathode, you're releasing OH minus, and so that obviously increases the pH. At the anode, you're reacting OH minus, so that would decrease the pH. We see when we balance out the reaction overall, there's no change in OH minus. So we're going to talk about pH specifically at the anode and at the cathode. So again, H plus is not released. It's more that OH minus is consumed. All right, so that gives us an example of relative electrode potential. Another example of relative electrode potential, and an example of when it works and when it doesn't work. NaCl aqueous, this is another very characteristic example of this type of problem. NaCl aqueous, you should know, is also called brine. So we're going to look at electrode potential and saturated solution. So we're going to use NaCl aqueous and do the same thing that we just did. We're going to do a nice little comparison here of who would win at the cathode, who would win at the anode. And so anode and cathode, cathode and anode, and my options here, I could have reduction of water. I could also have reduction of Na+. At the cathode, I could have oxidation of water. I could have oxidation of chlorine. And I'm going to write out these equations, decide who wins. So reduction of water, reduction of Na+, we just went through that. It's the same thing we did before because we're still looking at Na+ and water. So just like before, water is the winner. Now if we're looking at the anode, I look up water and chlorine. They've switched the signs in these reactions because they're writing out oxidations. Let me go ahead and use the data booklet here. So I'm going to look up the oxidation of water. I look for water being all by itself. And here's the oxidation of water. And then I also need to look for the oxidation of chlorine. All right, remind yourself, what's the rule? If I'm more positive, I am more likely to be reduced. More positive, I am more likely to be reduced. So more positive, more likely to be reduced. More negative, more likely to be oxidized. At the anode, I care about, or the thing that's definitely going to happen is oxidation. So between these two, water should win. All right, and I would expect discharge of O2 gas. So this is an example, water winning and discharge of O2 gas. This is an example of using E0 values, to find the selective discharge. Okay, relative concentrations. We saw one example of thinking about relative concentrations, and it's when something's very dilute. When something's very dilute, water wins. We can also have kind of the opposite situation. And what generally happens when I have electrolysis of NaCl, I'm going to get rid of this. What generally happens when I have electrolysis of NaCl is that I increase the concentration of NaCl. I make it greater than about 25% by mass. So you have a really, really salty solution. When you do that, even though H2O should win in terms of electrode potential, well, the thing that takes priority is the relative concentration. And what actually ends up winning is the oxidation of chlorine. And so instead of getting O2 gas, you end up getting chlorine gas. This has industrial uses, like it mentions here. Can be used industrially to get the discharge of chlorine. You have to use a high concentration to overcome what should happen in terms of electrode potentials. And so when you have a high concentration, you end up with chlorine gas getting released at the anode instead of the oxygen gas. Changes, well, we get chlorine gas and of course H2 gas. H2 gas is from water being selectively or preferentially reduced. The other thing to pay attention to here, this only affects chlorine. Water is still preferentially reduced at the cathode. Why? That's a long explanation. I'm not sure we have a great explanation beyond what you need to know, but this example of NaCl is one that you should definitely understand. And you should understand that at the anode, when we really, really increase that concentration of NaCl, we're going to force the system, instead of preferentially favoring oxygen production, it will favor the oxidation of Cl minus to make chlorine gas instead. You don't affect the cathode. You don't affect the cathode. You still prefer making the hydrogen over the Na plus. I suspect that it has something to do with how different in terms of the electrode potentials water and Na are versus water and chlorine. The water and Na are further apart. But this is an example you should be familiar with specifically. Chlorine gas, that's something you should know, has a strong smell. And again, we got an increase in OH minus. If we look at the overall reaction here, you get OH minus being produced, which will overall in the electrolyte lead to an increase in pH. All right, and just to quickly review that idea one more time in a little bit of a simplified diagram. So when I have saturated NaCl or brine, at the cathode, my two options are either water or Na plus getting reduced. Here they're just simplifying. They're showing H plus getting reduced instead of showing the full water equation. Water, of course, would dissociate to H plus and OH minus. And if it's not getting reduced, this whole process wouldn't happen. So I would just have some H pluses hanging out in solution from the waters that dissociated. Or the Na plus, of course, all of NaCl would dissociate to Na plus Cl minus. So either the Na pluses will get reduced or waters could get reduced. In this case, water, and this is a simplified version of this equation, you should show the full water equation, but in this case, at the cathode, water wins and hydrogen gas is evolved, always, regardless of electrode potential and concentration, etc. But if I get really saturated, based on electrode potential, water, they're again simplifying a little bit, just showing OH minus, which comes from the dissociation of water, and none of the rest of this reaction is happening. So water is just some waters will dissociate, just be hanging out in solution, or Cl minus. Based on the electrode potentials, the 2H2O yielding oxygen is what should happen, but if I saturate with enough NaCl, I can actually force chlorine to get oxidized instead. Well, when chlorine gets oxidized instead, my H2O, some of which have split up into H plus or H3O plus and OH minus, are just going to stay in the whole solution with everything else. Water itself won't react, so OH minus will be left over in solution. Notice I have Na plus from the NaCl that split up and didn't do electrolysis here. I have OH minus because water didn't do any reaction, so water is just staying as H plus and OH minus. And so when I have Na plus OH minus, I can get some sodium hydroxide being produced. And so that's why I would see an increase in pH of the electrolyte, because I'm not favoring water reacting and doing anything else, so I'm favoring keeping the OH minus in solution. All right, moving on to our last example here, and that is looking at CuSO4. So again, I have the same sort of setup. I'm trying to figure out who wins when I have CuSO4 in solution. So water is one option, of course. At the cathode, I could also get Cu2 plus 2 electrons, giving me copper solid. At the anode, I have SO42 minus that could get oxidized. Now, this is a little tricky, a little annoying, a little bit classic IB. You don't actually get this equation for SO42 minus being oxidized in the data booklet. And so it's actually water that gets favored here. Water is favored at the anode. How do you know that? Well, because I'm telling you, if you have some polyatomic ion and they haven't given you in the data booklet the equation, it's a good bet to assume that water is probably what's getting oxidized. That's the only thing you have information about. So that's really the only thing that you could assume. So in terms of who wins between water and SO42 minus, water wins, and so oxygen should be evolved at the anode. All right, looking at the cathode and who should win? Well, cathode, reduction, and remember I'm looking for the more positive electrode potential should be reduced. So when I look at the reduction of water, it is still negative 0.83. And even though I have 2 electrons here, I do not scale for number of electrons. Copper is positive 0.15. Well, okay, based on this, copper should win because more positive should get reduced, and reduction, of course, happens at the cathode. And this whole situation that we just talked about is true when we have inert electrodes. Inert just means not reactive, so that's going to be things like platinum or graphite. All right, so let's assume we change our electrodes to, instead of being made of platinum or graphite, my electrodes here are actually going to be made out of copper. Well, let's think about what could happen. At the cathode, still going to get reduction of copper. That looks great. At the anode, I can now actually get the oxidation of the copper electrode. So the oxidation of copper. All right, so now I need to do some preferential analysis to figure out, now that I have some copper available to me at the anode and not just water and SO42 minus, well, could copper actually be preferentially oxidized here? So oxidation of copper, what would oxidation of copper look like? Well, I have copper solid now available to me. That's my new anode. Copper solid could, of course, give me copper 2 plus 2 electrons. All right, well, let's look into electrode potentials, see if this oxidation of copper could be preferential over water. So copper, when I look it up in the standard electrode potentials, negative or plus 0.34. Of course, this is actually the one from the data booklet. So this is the one that I used to compare. I haven't switched any signs to account for it being oxidation. And water, when I look up the oxidation of water, water is a special one where I don't switch any signs. It just gives me the oxidation of water. Plus 1.23. Great. I'm looking for who's more likely to be oxidized. More likely to be reduced is positive. More likely to be oxidized is a more negative value. Interesting. Copper is the more negative value. So more likely to be oxidized. So once I have copper electrodes, I will actually get, instead of the oxidation of water, I am going to prefer the preferential, or the thing, the winner here is going to be the oxidation of copper. So what will that look like? Well, it'll look something like this. So at the anode, I'll get the oxidation of copper. At the cathode, I will get the reduction of copper. This can actually be used to purify copper. And so here I have copper solid. Some of the copper ions are leaving, and this helps get rid of some impurities. And then those copper ions that go into solution are then available for the reduction at the cathode. So another way to think about this is your copper ions from this copper solid here can replace some of the copper ions that are being used to do reduction at the pure copper cathode. So some observed changes. Well, on the cathode, we would actually get some copper being deposited. That makes sense because copper solid is being formed. And no change in pH of solution this time because I'm just dealing with copper and copper. No change in the intensity of the blue color because the ions that I'm forming here are the ions that are being used from the CuSO4 are being replaced from this impure copper anode. All right. And so, again, we have inert electrodes, we favor water. When we have copper electrodes, we actually favor the oxidation of copper in this case because copper is preferred over water based on electrode potentials. All right, there's a few examples here. I would suggest you look through these in the slides. You have both all of the examples and the answer keys available to you. Thank you for watching this very long video. I hope this helped. Have a good day.